It
Just a
doesn't.
second. Okay. Okay, good
I might.
morning, everybody. We starting the third day of Decision Camp, and our first presenter is Rob Parker. Rob is in Australia, and it's a midnight over there. So thank you, Rob, very much for joining and doing your presentation. This presentation would be about integrated use of decision systems that includes not only rules but also optimization software. And Rob, please tell us more about yourself and about your work. Thank you.
Sure. Thanks, Jacob. And good morning, good afternoon, good evening to everyone here, wherever you are in the world. As Jacob said, I'm currently just off the east coast of Australia, where it is just after midnight or very early on a Saturday morning. The presentation today, I'm going to be talking a little bit about integer programming. And if you'll just bear with me, I just need to reload so that I can actually see presentation myself. Okay, now, because I'm currently off the coast of Australia, I'm on a very low bandwidth signal. So what I'm going to do is, I hope you don't mind if I actually turn my camera off just to save bandwidth, and hopefully that will reduce the latency. Okay, so I'm sure everybody here is aware of the current excitement in AI, and I'm sure some of you here will be aware of integer programming. But did you know that Gartner recently published a hype cycle for technology in finance? And here's what it looks like. In particular, I noticed that AI is in the peak of inflated expectations, and that's going to be something I'm going to talk to today. Whereas driver-based modeling, which is a little bit of what I'll touch on this morning, or today I should say, you'll notice is now in that just coming up to the slope of enlightenment. So my name's Rob Parker. I'm from AngleFinance, and I'm here to talk to you about IP, intellectual property, or integer programming. Your organization needs both. So who are AngleFinance? We're actually an asset finance company operating in Australia. In terms of asset finance, we effectively provide loans to other businesses, in particular when businesses require capital for equipment, for modernizing or growing or extending their business, etc. They basically come to us as a financier to finance the purchase of equipment. Now, every organization has many easily accessible business optimization problems, and they're readily solved using mature exact methods such as integer programming. So using these methods, you can reduce costs, you can improve outcomes, and you can achieve this with the full transparency of the problem-solving mechanism without the vagaries such as the generative AI hallucinations. And so what's required to be successful? It comes down to three things using these exact techniques, so to speak. One, you need to search out these opportunities. So even though every organization is awash with these opportunities for optimizing problems and solving business problems, we find that the problem rarely comes looking for you. As I said, you kind of need to search through your organization or keep your eyes open looking for these opportunities. Number two, ideally you need your commoditized toolkit. And what I mean by that is not only do you need quite a toolkit of methods available to you, but you also need a very mature, very rapid capability to implement and model these particular problems. And the reason why is because the stakeholders, in my experience, they're more often interested in the outcome. They're very rarely interested in the actual underlying technology or the underlying mechanism. And so with your commoditized toolkit, it really helps if you can rapidly prototype, rapidly iterate, and rapidly converge on both a model and a solution. And lastly, you need a culture of open mindsets. So quite often when we come across these problems and you talk to a stakeholder, more often than not, they state the objective or the problem in the framework which they're currently using. or their kind of solution approach. And so again, using rapid prototyping and iteration and round tripping, we can help to tease out what the actual real problem is and what the real objective is. So today, I'm going to focus on some sample business problems where integer programming is a very good fit for solving these kinds of problems. Now, I'm sure that many people here would be familiar with integer programming, but just to make sure that everybody's up to speed, I'm just going to do a very, very brief recap on integer programming and how it works. So ultimately, it's underpinned by linear programming. And so we can define a problem as basically an objective function with many constraints. And as per the diagram on the left, those constraints determine what we call the feasible region. And we can readily solve that using linear programming, but we end up with effectively solution variables which are continuous rather than integer. And so what we can do then is with integer programming, we can use integer variables or variables where we want their value to be integral. So for example, the blue region here, it's showing effectively a feasible region where the decision variables are integer. And even more refined is we can use what's called 0-1 integer programming, where we can use integer variables which take on values either 0 or 1, and these can be used to make either true or false decisions, e.g., I want to invest in stock A or we don't invest in stock B. And in addition to that, there's what we call the branch and bound tree, which is a very efficient method for solving these problems. So effectively, we can use what's called the linear programming relaxation, which will give the feasible region and an initial solution where decision variables are continuous. And then we can gradually iterate over those decision variables and force them to be integral and effectively walk down the tree of combinations of outcomes, iteratively solving. And the great thing with branch and bound is we can actually cut off a lot of the search tree based on what's called the relaxation solution. I won't get into too much detail there, but that's basically a very quick summary of integer programming and what I'll be using today. And so what's the first problem we're going to talk to? It's rate card optimization. And so what's the actual business problem? And it's to construct an optimal rate card. In other words, what interest rate should we apply to each loan? And when you start talking to the users, the conversation typically goes something like this. The user, we want to optimize the rate card. So as an optimization analyst, we ask them, define optimal. And quite often the user's response might be, it's optimized. So one of the big challenges we have is there's a lot of impedance between the way a user describes the problem or their optimization requirements and the way we encode these in a model. So thus, this is again why I kind of talk about you need this ability to rapidly prototype and rapidly round trip as we iterate in with the user on, what is the real problem. So coming back to rate cards, we want to optimize it. So first of all, what is a rate card and how is it optimized? This is a typical rate card used in the finance industry. So again, on the left-hand side, we've got basically tiers of the size of the loan. And across the top, we've typically got the terms. So for example, in this case, we've got terms from 1 to 5 years, and you'll see the sizes of the loans. Characteristics of it. Ideally, it's very easy to read and very easy to understand for the market. So for example, if we look at the rates going from left to right, you'll notice that they are effectively monotonically increasing with regard to the term. So this is characteristic of a rising interest rate market. And if we go down the columns, you'll notice that they are monotonically decreasing. And in this particular circumstance, this might reflect effectively economies of scale. So there's discounting available as the loans get larger and larger and larger. So essentially, the rate card is what we expose to the market and what we expose to what we call our brokers. So they can readily look at the rate card and know what the anticipated rate of loan would be based on term and size. And sometimes the rate card might have other dimensions. This is a fairly simple one. Key message here is aesthetically, the rate card just looks right. And so now in talking with the end user or the stakeholder of this, we start to formulate our solution or the problem. And so with this particular one, we start with the inputs. So the first one is to build the optimal rate card, we need demand. So we need the expected volume by term and volume, and that's going to feed effectively, it's going to be a big driver of the cells, which are the rates. Next thing we need is the target yield or the weighted average yield. So effectively, the business sponsor is trying to achieve a particular outcome in terms of the profitability, etc. The next thing is what we call the yield curve. Now, this is some constraints we can put in which enforce that monotonically increasing or decreasing rates across the card. And these in particular, they really shape the rate card. And so with those three inputs, we build our optimization model, and the output or the desired output of the model is we want the optimal rate card. And again, that is effectively a rate card which reflects those shaping constraints, and in particular one which achieves that weighted average yield. With me while I go right. Okay, so looking at the demand model. In this particular circumstance, we don't need to synthesize a demand model. We've actually got lots of data on hand, and so we can use prior data to infer the demand model. Key takeaway here is it's highly non-uniform. So you'll see here in particular that, again, we've got the terms from years 1 to 5, and we've got our buckets of basically the tier of the loan. And so you'll notice that there's very little demand for a short-term loan of up to a year for a very high value in the order of $2 million. But we've got more and more demand effectively in that 5-year term down around about the $100,000 mark. And so that is our demand model. The next thing is our yield curve. So this effectively shapes the rate card. So we can realize the yield curve just by implementing constraints which enforce a minimum or maximum step size. So for example, we might often choose a step size of 5 basis points. And we use those constraints to shape the values in adjacent cells across the rate card. We can also add constraints which reflect a competitor's rates, such that, for example, we might want to match a competitor's rates or undercut them, etc. So we can actually also introduce some constraints which will enable us or a rate card to directly compete with the competitors. And lastly, the target yield is the last input. So some of you might ask, why do we need a target yield? Shouldn't the model actually optimize the yield? And ideally, this is true, but that would require a very accurate customer price sensitivity model. And sometimes this is unobtainable. So in other words, the ask of this, the model overall is given the demand and the constraints to shape the rate card such that each cell in the rate card differs by a consistent 5 basis points. Find the rate card, and in this case, in the absence of a price elasticity model, we might ask for a rate card which has the lowest highest rate, which also meets the average weighted yield. Okay. So that's requirements, and this is a more a formal write-up of the actual mathematics behind the model. It's not the complete model; it's a bit of a snippet. But we could start by writing this up. However, users typically want to see results, and they really tend to, their eyes glaze over when they see this kind of write-up of a mathematical model. But just to quickly go through it, key takeaways here is it's using integer decision variables. That's the denoted xt, which is the decision variable for term t and exposure e. It's a minimax objective, so that reflects that we want to minimize the maximum rate across the rate card. We've got another constraint, which is we want to achieve at least the weighted average yield, and then we've got our yield curve constraints, which basically introduce those step sizes, et cetera, et cetera. And so you might ask the question, why use integer decision variables for these actual rates? Why not just use continuous variables? And we could, however, when we solve it with non-integer variables, we might get values, which is, for example, a rate might be 3.14159.265, or in other words, 15 decimal places of accuracy. And again, it comes back to the aesthetics of the rate card. So by constraining these decision variables to be integers, we can, for example, rather than it being 3.141, it would be 314. And so by using these integer variables, we can constrain the granularity of the rates such that we don't get some very obscure looking numbers. And again, this is why we need that objective function to have a target yield at least as high as the desired yield. But we get as close as possible to that by also minimizing the maximum rate. Okay. So in solving this, we can readily solve it with a standard integer programming solver. And so this is a sample rate card generated by the model. As key takeaways, we've got that monotonically increasing, decreasing rates across the card. The target minimum yield or minimum weighted average yield for this particular model was 8%. And the outcome of the model is it achieved a weighted average yield of 8.03%, so it meets that target. And the other key takeaway here is you can see that the maximum rate is 8.45, which is the $5,000 tier in the 5 years. So some of you might ask, why is the solution average yield not the same as the target yield? And again, this is coming back to the granularity introduced by those integer variables to get those kind of like nice looking numbers with only 2 decimal places, but again, kind of nice looking that they're not obscure numbers. It's not necessarily the case that it always needs to be, rates such as in increments of 5 basis points, et cetera. This one just happens to turn out that way. But again, sometimes we want the rate cards to be what we call this aesthetically pleasing. And then once the user gets an appetite for this, they can kind of say, but wait, there's more. They actually have a new objective. And so in this particular case, the user says, but can we actually add a component which reflects the price elasticity of demand relative to the rate? And we can. The answer is yes, we can. We can introduce a price elasticity curve. We could use an assumed model where our rates are higher. We tend to lose customers. However, rate differentiation is not the only selection criteria. So looking at this curve here, we've got an assumption that where our rates start to get higher than competitors, we will lose them. So we get that trend down. However, we won't lose 100% of market share because there's other reasons why borrowers might choose to stay with us. So looking at this curve for price elasticity, we start to get that inflection point basically around in this particular model, 8%, which might reflect where the competitive market is. You'll start to see that demand, we start to attenuate the demand, modeling the price elasticity. And a lot of people might be surprised that with linear programming, they'll say, oh, but aren't you restricted to linear kind of constructs, et cetera? And this is a highly nonlinear curve. So what we can do here is we can use a piecewise linear approximation. So we can approximate the curve with multiple linear pieces. And using this technique, we actually introduce additional decision variables, which are zero and integer variables, and they reflect, for when we're solving the solution, which part of that linear approximation you're currently operating in. And now, as a consequence of having this price elasticity model, we can change the objective. So rather than minimize the maximum rate subject to at least the target yield, we can actually pivot across to maximize the yield subject to our price elasticity attrition model. And you can see how it works in the mathematics. So we've still got our demand based on the exposure and the term. We've got our decision variable, which is the X, and we've just introduced the attrition, which is depending on what the value of X is. Using that piecewise linear curve, it will actually start to reduce the demand. So we still use the yield curve constraints to get that monotonically increasing, decreasing. And in this case, we don't use a minimax anymore in terms of the prior model. In this one, the elasticity model will drive towards minimum and maximum rates. And so as a sample result, we've got the desired rate card shape. We can see that the weighted average yield and the minimum and maximum rates. So in this case, our weighted average yield was 7.9%. Remember, we haven't set a target yield for this one. This is based on the price elasticity model. And the other key takeaway here is from the model, we can actually see that we lost 90% of the demand based on our elasticity model, and that occurred in the 5-year term $5,000 category. And again, this is just an indicative model, but what this enables the users to do, and again, you need this rapid prototyping and rapid turning around, the users can do quite a lot of what-if analysis. So it gives them a sense of sensitivity to the different parameters, etc. I do notice, Jacob, you've asked a question on what linear solver did we use. In this case, I'm just about any solver will do. These results came out of Skip, which is one of the open source solvers readily accessible to everyone. So that's a problem to do, or a relatively simple problem to do with optimizing rate cards. So what's another business problem we can solve? And again, these problems don't come to you. You kind of have to go searching for them. And this one is with regard to our treasury function. And in particular, their requirement is create an optimal securitization pool cut. So I just need to do a quick segue into loan securitization. So effectively, as a financier and following the steps here in step 1, we lend money to the borrower. So the borrower receives money, step 2. And in return, as the borrower pays back the loan, step 3, we receive principal and interest. But in step 4, what we can do is we can take all the loans on our books and start to aggregate them into a financial security. And with that financial security, we can sell that to investors on the money markets. And effectively, the investors will purchase that security from us, which means funds flow back into us. And the reason why we do this is because we have limited funds, it actually enables us to keep lending. So effectively, we keep on topping up our capital by this securitization mechanism. So the benefits ultimately for us is, again, it provides us with liquidity. The benefit for investors is it provides them with a income stream and a place to invest their surplus funds. And in addition, for us, it can actually reduce the cost of funds as we secure or securitize many loans. Now, there's one other variation of a security instrument, and it's called a funding warehouse, which is very similar to this concept. One of the main differences is a funding warehouse, you can think of it as a line of credit. so it can be progressively drawn down. But some of the conditions of these funding warehouses is they must have a diversified set of loans behind them in terms of asset backing, and that's purely a risk posture. So by having diversification, there is effectively reduced risk. So that's securitization. So in terms of the business problem or the decisions available, again, I mentioned earlier that organisations are ripe with candidate problems. If anyone has been involved in mining operations or mining ore optimization, this will be very similar to ore blending. And so types of problems here is for building the financial instrument in the first place, we need to decide which loans to transfer off our ledger and bundle into an asset-backed security to be sold. There are alternate problems, which is we might have a couple of funding warehouses and we might want to decide which loans do we transfer from one funding warehouse to another funding warehouse in order to create headroom. And yet another problem is you can progressively draw down funds from these funding warehouses, but there's penalties for underutilization, and there are effectively constraints on how often you can draw down on these funds. So yet another optimization problem is the rate at which we can draw down on these credit problems. So again, just many samples of problems. But today I'm going to focus on deciding which loans to transfer from one funding warehouse to another for a sample problem. And so what's the problem? A financier like ourselves, we might have many of these funding warehouses. Different funding warehouses have different constraints on diversification. And as we start to consume the capital available in these funding warehouses, effectively we start to run out of headroom. So a common use case is we might have, say, 2 funding warehouses which are starting to be consumed. We establish a new funding warehouse, and effectively to create headroom, the challenge is to select loans from your existing warehouses and bundle them up and transfer them into the new warehouse. And so what that does is it actually creates headroom across all of the warehouses. But this is all, again, subject to constraints. So we've got diversity constraints. And what I mean by that is there's industry diversity. So, for example, across a given warehouse, no more than X% of your borrowers can be from industry X. No more than Y% can be from industry Y, etc. We've got geographic constraints. So no more than X% of the portfolio can come from this particular state or region, etc. There are lots and lots of measures in terms of what dimensions go into these diversity constraints. And so to solve this particular problem, which is to transfer out of one funding warehouse to another warehouse, it's a classic 0-1 integer model. So we can set up integer variables where effectively 1 means or you transfer the loan out of its existing warehouse to the new, and 0 means we don't. And so in the first iteration with the Treasury analysts, it becomes apparent that maybe the optimal thing they're trying to do is they set target values or target amounts of drawdown for each warehouse, which or in other words, a target capacity utilization. So, for example, this warehouse, it might be $200 million. This warehouse is $250 million, and for this particular the new warehouse, it might be $200 million. So we might think that the objective function is effectively we want to build up the warehouses and transfer loans across and get as close as possible to those targets. And once again, we start thinking about one of these minimax problems where we want to minimize the maximum deviation from the target warehouse capacity. And again, this is subject to maintaining those portfolio diversity measures within target ranges. And we want to maintain warehouse capacity utilization constraints. So again, even though we might have the target, we have to make sure that we don't exceed the actual capacity of the warehouse. So that's very briefly that problem. Again, models and inputs. We start with our current warehouse utilization. We've got our capacity and diversity targets. We've got our additional warehouse. We put that through our model, which is our 0-1 programming. Choose, it's effectively a set partitioning problem you might think of. So it's choose those loans which we're going to transfer out of their existing warehouse into the new warehouse. And in terms of the output, effectively we want the optimal warehouse allocation, and it will free up additional funding headroom. So very easy to run that problem. But it turns out, and again, this is where this iterative round tripping occurs, and it also reflects the some of the challenges in our end users or stakeholders really articulating the problem statement. So it turns out that that simple problem is actually not the real objective. So the problem is readily solved. However, to the Treasury analyst, they not only want to create headroom in terms of the capacity of the warehouse or the capital involved, it turns out that those diversity constraints, they also want to create headroom in. So for example, one of the characteristics of linear programming or integer programming is whilst it produces the optimal solution or the optimal outcome, it will tend to produce solutions which are at the extreme corners. So for example, in this case, in minimizing the maximum deviation from the target warehouse capacities, it comes up with a very good answer, and in fact, a provably optimal answer. The challenge for the Treasury analyst is in terms of diversity constraints, sometimes the solutions were right on the boundaries of the limit of those kind of constraints. So for example, if say 30% of the portfolio or no more than 30% of the portfolio could be concentrated in any particular geographic region, then again, the optimal solution in terms of the capacity utilization might end up with a solution where the geographic diversity is right on that border. And so it turns out that that's really not what the Treasury analyst wants. What they want is they want headroom across not just capacity, but also those utilization or diversity constraints. And so that's what causes us to revise our model. And so again, we have a minimax problem, but what we do here is not just minimize the maximum deviation from target capacity, but also minimize the deviation from their diversity targets. And again, we do this subject to maintain portfolio diversity measures across target values, etc. And so in summary, whilst AI is trending, there's still life and reward and business value in what I call these more traditional techniques. There are candidate business problems in every business. They're awash with them, but as I said, often they won't come to you. You actually might need to seek them out. And iteration, experimentation, and rapid prototyping are necessary to find the real problem because, again, as I mentioned, sometimes our stakeholders, they frame the problem or in their current solution space, and getting them to articulate what the real objective is can be quite challenging. So that's my experience with integer programming in organizations. Any questions? I just have a quick look at the chat. Is a monotonic increasing, decreasing a constraint from regulators or a desired attribute? Yeah, it's definitely a desired attribute. So again, you might understand that the rate card to some degree reflects a pricing of risk. And so as rates are going up in an increasing market, there's an expectation that the rate card will reflect that. So as the term goes from 1 to 5 years, we see rising rates. It doesn't have to be monotonically increasing. It could you could have risk-based pricing due to certain market conditions where it's not monotonically. But in this case, this was the desired characteristic at this particular point in time. Again, with the modeling approach, we could tune those constraints to effectively achieve any shape or any desired shape which our stakeholders wanted to achieve. I think, Jacob, you asked about linear solver.
Yes. No,
so
it's okay. I just put list of the Romania solvers and doesn't matter. They all probably will work. Your problem is not really big size problem, right? You don't need a commercial power solver like Gorobi or
no,
Simplex.
definitely not. To give you an
Yeah,
example,
we have,
an example of loan securitization, typically they're actually quite large problems in terms of number of variables. So at any given time, we might be dealing with a portfolio of 20, 30,000 loans which need to be petitioned.
That's a lot.
It's a lot of integer variables. But even Skip running on a basic laptop, it can solve that in about a minute. So 30,000 integer variables, it's a fairly easy problem to be solved by Skip or linear integer programming. Yeah.
Yes, we have similar experience with Skip, with Coin, with JLPK. They all quite good.
Yeah.
And I wonder, title of your presentation was intellectual property or integer programming. Your enterprise needs both, and you did not explain. What do you mean?
So the technique is, integer programming. Key takeaway there is it's still such a useful tool in so many problem domains available in every business. And the intellectual property part of it is effectively, the formulation of those models, having in your toolkit, those minimax capabilities, piecewise linear approximations, etc. And so the intellectual property is effectively applying those to your particular solution approaches for your particular problems in your enterprise.
Yeah. Any questions from other people? I will ask one more question.
Yep.
This is just more theoretical presentation or promotion of linear programming. You do have real world client. I'm not sure if you can disclose a name, but is it in production or is it just research?
So these ones are ones I've done internally for AngleFinance. So that's, we use them internally. These particular models, they're a little bit cut down from production. The production ones are slightly more complicated. In particular, the loan securitization or the warehouse funding optimization, that is a model which is actually currently being worked on by an external party who are potentially embedding this type of model into a software as a service solution for treasury management. So we do use these models internally to some degree, and we're seeing similar type approaches being implemented in external party packages. Yep.
I see. Your message basically is that IP is still IP. It's not IP. It's really integer programming tools. It's still very powerful and still underestimated. And I remember we tried to do similar things, by the way, in Australia and Westpac Bank. And I remember resistance. They told this is beautiful, but the rules-based is sufficient for us. If you we will give you a few rules and we will tell you how better to select the proper rate, for example. And so do you think, it was 20 years ago almost, and situation does not change, right? Optimization still is not really welcome in big companies.
Absolutely, and that's why I kind of talked about you need the ability to rapidly iterate. And like I said, if I show an end user the formal mathematical model in terms of the, sigma, et cetera, their eyes glaze over. Most stakeholders, in my experience, they want to see the result. And quite often the elegance behind the model and the solution approach is less important to them or less visible to them. They're really results oriented. Yep. And the other challenge is quite often, as I was saying with the securitization one, their definition of optimal or their objective function can quite often be quite hard to actually tease apart. And more often than not, it's a multi-objective. And then the challenge with the multi-objective is we start getting into weighted multi-objectives. It's like, what's more important? Classic case in that Treasury repetitioning or creating headroom in the portfolios. It's kind of like, okay, we will minimize maximum deviation across multiple dimensions, but the magnitude of them can be different. So is it true that they're all created equal, or do you want to actually bias them? And again, in that particular case, what was necessary was to do a lot of iteration and a lot of round tripping and a lot of trial and error to actually just try different weightings until we came up with a model which satisfied the analyst's desired outcome.
It's almost always problems like this, the multi-objective optimization, and I want to make just note that from real-world experience that it's much better not to promote optimization as a separate technology. If you incorporate optimization inside Decision Intelligence Toolkit, and you can do all of them, sometimes you need not linear but constraint solver to solve some and split problem to a lot of automatically split to a lot of linear problems, and then combine results again, and constraint solver is perfect for this. But before you even go to constraints, you need to select, for example, weights for different optimization objectives, and business rules perfect for this. And when you, if you as a guru in optimization do all work, they would never buy it. But if you let them do this work using very friendly decision modeling environment and just hide your optimization as a one little module inside, it would be much, much more productive. That's what. That's why today we're not talking about rule engine or optimization engine. We're talking about decision engines that can utilize multiple solving techniques without bothering customer with all even modeling details like this. So I tried in my scheduling presentation, you saw that I completely tried to hide how to solve it. Even modeling part is just stay as close as possible to business. Maybe you can you can do something similar. But anyway, it's a very good presentation. Thank you very much.
Thank you, Jake.